Okay.
Hi, everyone. Hello, good morning, good evening, good afternoon, wherever you are. It's our pleasure and honor to host you this week again with another Geoscience and GeoEnergy webinar, actually the last one in the year of 2020. I wish all of you are having good time and joining us more and more with your friends and colleagues next year too, as we wish to continue this initiative for years to come. As we get also close to the end of the year, Sebastian and I would like to ask you all, please record yourself for 10 seconds, send the record link to the email address that we would type in a moment in the chat box. We will collect all your 10 seconds Happy New Year or introduction of yourself, what you do, where are you from, what brings you here to be with us together, and we will cluster all these clips together, release it next week, hopefully, or in 1 or 2 weeks to come. So please do send your video, so be featured in this channel, so let everybody know who you are, what you do, and what makes you happy in geoscience field. There is also a Tea Time Talk series established for allowing junior researchers, PhD and postdocs to build up their professional network. Do attend, volunteer to present your work and establish your friendship and a network at the very early stage of your professional career as well. So without any further ado, I would like to have the pleasure and honor to introduce our last speaker of 2020. We have today with us David McNamara from Liverpool University here with us. I'll introduce him to you all. Those who don't know him, those colleagues and friends who are watching him already are so happy and grateful to have him with this very nice and entertaining background that he has actually here. So great actually to see that quite energetic scene on the background too. I hope it's not too much distracting for the audience, so they will follow the geology as well, but we will do our best, David, so you can check. Okay. So David is a structural geologist at the University of Liverpool, Department of Earth, Ocean and Ecological Sciences. He graduated with a Bachelor of Art in Natural Sciences from Trinity College, Dublin. And from there, he went on to complete his PhD at the University of Liverpool, where he is working today, working to understand the micro-deformation processes of rocks in the Italian Alps. After finishing his PhD, he took a position as a research scientist and consultant in the Natural Resources Division of the Institute of Geological and Nuclear Sciences in New Zealand. In New Zealand, David developed an expertise in geothermal borehole logging and geomechanics, which he used to assist government agencies and energy companies develop geothermal resources in New Zealand, the USA, Nicaragua, and Indonesia. David further developed his research in subsurface structure and stress characterization to become involved in the New Zealand Deep Fault Drilling Program, which drilled the Alpine Fault to understand its structural architecture and assess the earthquake risk of this plate boundary fault. David's research in geothermal subsurfaces also expanded to other aspects on the energy sector, including research on the geomechanics of New Zealand's petroleum resources and exploring the role faults play in CO2's capture and storage. Currently, David is engaged with research into the link between structure, stress, fluid flow, and slow slip earthquakes at the Hikurangi subduction margin in New Zealand, the geomechanical controls of CCS in Ireland, and in the macroanalytical determination of fracture sealing mechanisms in energy critical resources such as geothermal reservoirs, CCS reservoirs, and or bodies containing energy critical elements. He has received a number of awards. I would like to list a few here. He's adjunct professor also at Reykjavik University, honorary research associate of Victoria University, Wellington. In 2014 is another award he has received. Royal Society of New Zealand's President Award was also offered to him in 2011 from Royal Society of New Zealand. He also holds Edge Prize from Trinity College, Dublin as well. What a career, David. So it's, we are glad, pleased, and honored to have you here. Thank you very much for graciously accepting to give this very last live webinar. And to the audience, please note David's lecture will last for about half an hour. Like always, my friend Sebastian Geiger would chair the discussion session after the talk. Please do not wait until end of David's talk. Post your questions as early as you can, because it might also stimulate other questions from the audience. We are looking forward to have a lively discussion at the end. Without any further ado, David, the stage bandwidth, the screen is all yours.
Thank you so much, Hadi, for that introduction. It's really crazy when you hear it back to you sometimes, the number of things you're involved in. And I guess it's an interesting place to start, and something that I always try and sort of carry across when I give a talk is that I've worked on energy systems and mineralogy systems and hazards, and it's all from a structural geology perspective, I guess. And I hope if a good takeaway, I guess, from that is that the skills and the techniques that we develop as geoscientists are so transferable to lots of really important things that we need to study about the planet. So I hope that sort of diatribe of things that I've been involved in maybe exemplifies that a little bit. I'd also just say thanks for pointing out some of the awards as well. The President's Award from the Royal Society of New Zealand was amazing, but I want to make sure that it's known that was shared by myself and an amazing group of people that I worked with in New Zealand as well. And it wasn't just me on my own. And I guess with that said, it's important to introduce my talk. And I think you can see from the first slide, I'm a big fan of not doing science in isolation. And I believe that the best science is done when it's done with people. So I just wanted to list a lot of amazing, talented and fantastic researchers and industry scientists that I've worked with over the years, all of whom contributed to some of what I'm going to talk to you about today. So a huge shout out to all those amazing, wonderful people that I've had the privilege of engaging with over the years. So I'm going to talk today about how I have been working for the last 10 years or so in the geothermal energy sector in an effort to establish the controls on fluid flow in these systems contributed to by the structure of these systems, the structural networks and architectures of geothermal. When I talk about geothermal energy, I always start from a position where I think it's really important that we view geothermal energy for what it is, because it's very easy to think about energy just as a source of electricity, but of course energy is a much broader concept than that, and geothermal energy lends itself very nicely to that broader concept of energy. So not only can we use geothermal energy to generate electricity, where we use the hot fluids and steam to drive turbines. And there's a nice example here of the Wariki geothermal field, Borehole, where I've done a lot of my research in. Geothermal is also really useful in a direct use kind of sense. So we can use smaller scale geothermal systems to power or use or provide energy that heats or cools our houses. And there's also lots of really interesting industry applications for geothermal that happen on small scales as well. Anything from bathing, tourism, timber drying, or agriculture, aquaculture itself. So as a structural geologist, I think it's really important to frame my research with understanding why is structure important to geothermal systems. A lot of the geothermal reservoirs that we try and access fluids from, not all of them, but a lot of them, are hosted in rock that has low intrinsic permeability. So it often doesn't have a lot of great interconnected pore spaces that allow fluids to circulate or transmit through those rock volumes. And then because of this, a lot of the reservoir types that we're dealing with, the performance and the operation of those systems relies very heavily then on fluid being communicated through brittle structures, so fractures and fault networks. And these are just some examples of some of those here. These are some lava flows that are analog outcrops for lava-hosted andesite, or sorry, geothermal reservoirs hosted in andesite lavas in the New Zealand fields. These are some core from the actual andesite reservoirs themselves. And you can see the heavily structured and mineralized structured nature of those fracture networks that facilitate the geothermal fluid circulation in those systems. And then we also have things like basement rocks, so schists and greywackies and other types of very indurated and hard, low porosity rocks that are also great reservoirs in a number of places for geothermal, which again heavily rely on fracture networks. So here you can see in this diagram over here, this is an example of the Greywacke basement rock of New Zealand, which is also a good host for a number of geothermal resources across the country. And again, very hard to put fluid through the intact rock, but when you fracture it, it becomes an excellent fluid flow system. So being able to understand those structural networks and understand how they contribute to the fluid flow or control or manage the fluid flow is a really important thing if we want to be able to work with these systems efficiently, environmentally, and sustainably. So that's where I've been focusing a lot of my research over the last while, is developing the structural geology associated with geothermal energy systems. And that, of course, spills then into understanding not just structural geology itself, but combining that with other elements such as stress fields to understand geomechanics. And when I started working in New Zealand in geothermal in 2009, 2010, I realized that what we really needed to do a lot more of was to really characterize the geology of these resources that we work with, particularly the structural geology, which can be quite difficult at times depending on the method you're trying to use. And that we also needed to do a better job and a more detailed job of understanding and characterizing the stress fields that these systems operated within. And there's been great examples of other geothermal systems where that's been done prior to that. So if you look at some of the geothermal systems in California, Nevada in the United States, or in Sulfure, for example, amazing jobs of combining these really essential properties. And this is something I wanted to sort of develop more when I started in New Zealand, because I seen it as a knowledge gap that we had existing there. And that's where I got to work with GeoScience, and that's where I got to work with the energy companies in that space and grow my career in that space. So that's what I want to talk about today is what we did in the New Zealand systems to produce more detailed geological models and to characterize the stress fields and combine those to provide us new insights into how these structural geothermal systems were controlling geothermal fluid migration. So a lot of the systems I'll talk about today are hosted in what we call the Taupo volcanic zone. So the Taupo volcanic zone is a back arc rift in the North Island of New Zealand that sits just above where the Pacific plate is being subducted underneath the Australasian Indian plate here. So it's a rift that's aligned northeast, southwest, and it's extending northwest, southeast. And it's an interesting rift because it has some very interesting dynamics that go with it. You can see that it's wider at one end than it is at the other because there's a rotational effect occurring on this rifting process as well. So it opens at different rates as you move along the rift axis. There's been a lot of really great research that's gone into understanding the interplay between volcanism, tectonics, structure, and geothermal expression in the Taupo volcanic zone over many, many decades, of which I'm happy to have now been able to contribute to myself. And when I started working in it, one of the sort of bigger conceptual models we had for how the big scale structure, tectonics, and geothermal expression sort of linked was summarized in this map diagram here. So what hopefully you can see from this diagram here is we have the edge of the Taupo active modern Taupo rift here itself, and all of these red lines that I'm just emphasizing here, these are the mapped actives, or were the mapped active structures that we had observed across the system. So these are the active normal faults that we see. And you can see from the trend of those, the direction is pretty consistent with the axis of the rift itself. And these are dip-slip faults, so they're either dipping in a northwest or a southeast direction. When we look at the changes in dip direction, and this is work that was pioneered and done by Julie Rowland at the University of Auckland in the early 2000s, they characterized where the dominant dip directions of these active fault systems changed, and they were able to use that information to infer the locations of the rift axes along the Taupo volcanic zone itself. And what they were able to see from the pattern that kind of came out of that data analysis was that the rift axis seems to be offset in multiple locations across the rift itself, and that some of the offset or this assumed northwest southeast oriented offset of these rift axes seems to coincide with where we get geothermal expression. So you can see here the main geothermal fields of the Taupo volcanic zone, and these orange outlines, these are identified by resistivity. You can see that a lot of them seem to fall where we get this intersection of the rift structure trend, which is northeast southwest, and these interesting offsets or apparent offsets in the rift axis itself. And the concept here was that we're getting geothermal expression in these locations because we're getting structural complexity by combining two sets of orientations in a massive way across this large scale rift. And when you have multiple fault and fracture orientations crossing each other, you increase the structural complexity. If you increase the structural complexity, you increase the connectivity of the structural network, which increases fluid circulation. So that increased fluid circulation brought about by the structural complexity in these zones is one of the ways we think, is one of the working concepts for how and why the geothermal fields appear where they appear inside this rift. And this was something I wanted to explore a little bit with some new data and techniques that we brought to bear on the Taupo volcanic zone and its geothermal systems. So we've been mapping faults in the New Zealand geothermal systems for a long time, since the 1960s. This is a workup of one of the original maps that was done by Grindley back in the 1960s itself. And this is a fault map of the Wairiki geothermal field. So we're going to look at this geothermal field down here. This is the one I've done a lot of work on. And what we can see from the mapping that was done back then is indeed we have a lot of these active faults and mapped structures with this nice northeast southwest trend to them, which is what we expect. This is happily sits within our understanding of the larger scale rift pattern. But what we can also see, even as far back as the mapping that Grindley done, is there are other orientations of faults that appear throughout these systems. We can see east-west type structures. We can see northwest-southeast oriented structures. So the structural complexity is interesting at multiple scales, and that scale of complexity needs to relate in some way to the large-scale rifting processes that are going on. With the mapping that was done in the 1960s, we've actually taken that and advanced it further using a combination of techniques and also bringing to bear some new techniques for mapping fault traces out on surfaces, including everything from digital elevation models to aerial photography, that kind of thing. And we've generated new active fault maps of the Wairiki geothermal field. So here is a map of the active structures from a recent paper published last year, which I'll talk more about later. And this is the resistivity boundary of the Wairiki geothermal field. And these are some of the wells, wells that have been drilled for injection and productivity in this field itself. And we mapped a lot of the active structures across this, adding to what Grindley had already done and what other people had already been building over the decades. And what we were able to see is not only are we getting those nice north, east, southwest trends that we're expecting, but what we're seeing is actually those sub-trends of east-west structures are actually a little bit more present in this field than we thought they originally were. There's actually quite a lot more of these east-west structures occurring. We are also able to analyze the dip direction of these as well. So those that are dipping northwest have colored blue, those that are dipping southeast have colored red. And you can see that the dominance of dip direction of different structures isn't as straightforward as what we maybe originally thought, which is where the current conceptual model has sort of, some of the underpinning aspects of the current conceptual model have come from. So it's interesting to start rethinking some of our ideas about how these systems work in a rift manner from new data that we're acquiring. So we also can go in and ground truth some of this information. So we do that by going in and trenching across large scale structures. And that's an example of the image I'm showing here. We can see these nice trenches where we can analyze things about the fault, their rate of activity, their orientation a little bit better. So we're combining modern techniques and remote sensing techniques with more field work and trenching aspects as well, completing or generating a more robust structural map. We're also able to do a lot of really cool things with modeling and computer geoscience these days as well. So, for example, this is a geological model, three-dimensional geological model that has been built from the geology of the wells that have been drilled in the Warwick geothermal field over the decades that it's been in operation. And you can see we can build quite a complex model from just looking at differences between thicknesses of geological units between wells, offsets between the same geological units between wells, and it allows us to get a sense, and it allows us to extrapolate sensible structural patterns throughout this geological field. And that's what we've done with these models, this model here of the geothermal field. You can find more information about that in this paper down here. And we can put that into a nice trace fault map with dip direction as well on these systems. And again, this is just another way of adding more information, adding more structural information, and refining our characterization of the structure of these fields, using more and more techniques that are coming on board as the industry advances and as the research into these systems advances. And from the modeling, we get a trend that is unsurprisingly dominantly northeast southwest in terms of the structures that help make sense of the geology that we observe in the wells. So again, it's matching that rift trend that we observe. Then, of course, there are geophysical methods for getting a sense of structure as well. And these help us get insights into possibly some of the deeper structure that we're looking at. So, for example, we have used microseismicity in the Warwick geothermal field to analyze locations of earthquakes to see if that helps us identify structural trends or fault trends that might be active in the subsurface around the geothermal center. And this is fantastic work that was done by a colleague, an industry geologist, Fabian Sepulveda. And what we were able to see from this analysis is that we're getting structures that are nicely in line again with the rift trend that we expect. At depths of 6 kilometers, which is great. And what we're also seeing though is northwest southeast trends that we can pull out from the concentrations of earthquake patterns, and also get a sense of really deep structures and dip directions due to clustering. So our microseismicity is also helping us build at this larger scale and deeper structural picture of the structural architecture of the rift and thus the geothermal systems in them. Other larger scale work, again, can be done by using things like magnetotelluric surveys. And this is an amazing piece of work that's been done by Ted Bertrand, a former colleague of mine at GeoScience in New Zealand. And again, they're using magnetotellurics to try and capture the presence of fluids and whether they are potentially structurally controlled at large scales across the rift itself. So what you can see from this model here is I have my northeast southwest direction in this way, and you can see here my geothermal fields nicely lining up along the northeast southwest trend of the rift. But then we also have these large scale dipping structures underneath, which might be representing large scale deep faults that allow the channeling of fluid, of hot magmatic and circulating hydrothermal fluids through this 6-10 kilometer deep system, feeding our geothermal systems at a shallower level. So we're really pulling together as many different techniques as possible to try and get that much more detailed structural picture of our geothermal systems. So now I want to talk a little bit about what I contributed to that, because a lot of what I've shown you, I've collaborated with these amazing people, but that's all their excellent research. Something that I've specifically worked on is the detailed level and smaller sort of scale level of structure that are inside our geothermal systems. And that comes down to characterizing the fracture networks that exist within those and how they channel the fluid flows. And one of the problems that had been in New Zealand geothermal for a long time was that we had very little access to analog outcrop material where we could measure fracture properties and fracture statistics from outcrops that would resemble what might be in the subsurface, because there's very little of the standard reservoir rocks in the New Zealand geothermal systems exposed anywhere. They're all buried within that rift itself. Another problem we had is it's really hard to capture the larger scale structure with seismic surveys, for example, because of the silicic composition of a lot of the rift infill material, the volcanic clastics, the rhyolites, etc. It attenuates that signal, so we don't get very good seismic profiles either. And one of the ways to try and get around that, and especially to characterize the fracture scale networks in these systems, is to use borehole imaging. But again, we had issues with doing this in geothermal, but these were of a technological nature instead. And this was a real shame because borehole imaging is a great way of being able to analyze a lot of really detailed fracture data in a fractured reservoir. So for anyone that's maybe not familiar with borehole imaging, there's a couple of different types we can do, but they're basically tools that we lower into wells that use either acoustics or electrical resistivity variations of the geological features along that well to create false images of the geology that are completely oriented with respect to north because the tool contains three-dimensional magnetometers inside it to keep it oriented. What this basically means is we can take those images and we can use software to analyze the orientations of structures, the density, the aperture or width of those structures. We can do a lot of really great structural characterization in a sort of semi 2D way along a geothermal well in a reservoir. Now, the application of that technique is certainly not new to geothermal systems. It's been done again in other systems, for example, by people like Nick Devazis, Colleen Barton, Steve Hickman in the COSO geothermal field, and by people like Crystal Dozaez and her team in Sulfure, for example. So it's not an uncommon technique to have been run in New Zealand, to have been run in geothermal in general, but in New Zealand we weren't able to. And that was mostly because the geothermal wells that are being drilled in New Zealand often go to depths of 3 to 3.5 kilometers, especially in the more modern stages of drilling. And the temperatures that you're experiencing there are anywhere from 300 to 350 degrees centigrade. Most standard industry tools for acquiring borehole images basically have temperature ratings of maybe 175 degrees centigrade. So it becomes impossible to run them in these high temperature wells because you will just fry the technology and it costs a lot of money. So industry isn't really interested in running the risk of that. However, that was recognized by a European consortium in the probably late 90s, early 2000s, and they developed a whole suite of new tools that were able to operate in high temperature geothermal wells and systems. And one of the tools they developed was a borehole acoustic televiewer. So it's using acoustics to generate borehole images. They developed it for geothermal wells specifically, and it was rated to roughly about 300 degrees centigrade. This was the ABI 8592 acoustic borehole televiewer. It was the developed product was trialed in an Icelandic geothermal well and then rolled out for the first time for industry purposes in New Zealand by a company called GeoEnergy, who had sort of branded it as the Acoustic Formation Imaging Technology Tool, or the AFIT tool. And that tool entered the New Zealand sort of industry space around about the end of 2009, which happily coincided with my arrival after my PhD in New Zealand to GeoScience. And combining the two, myself and my sort of self-classification as a structural geologist and this new tool, the company put me together with the energy industry to start analyzing the very first data sets that we were acquiring from these images and to see what we could figure out about our geothermal systems based on this new technology that we were applying. So since 2010, when we got the first data, we've run this tool in 30 different wells across about 6 different geothermal fields in the Taupo volcanic zone, and I've highlighted those in green here. It's provided us with really interesting information on structural orientations. It's given us our first direct observation of structural orientations in the deep geothermal systems, circulating systems. It's also provided us for the first time actual characterization of horizontal stress field orientations in these systems as well. And now that we're starting to run other types of imaging techniques, we're starting to get a sense of the lithological textures of these volcanic clastic units and lava units that host the geothermal systems as well. When we take a lot of that information and we combine it with pressure and temperature and fluid velocity and well testing data, we're now able to actually start saying something directly about how structure is influencing permeability in our geothermal fields. In the last few years, we've also been developing techniques for running resistivity imaging in these tools as well. So we're able to complement the acoustic images with resistivity, which involves things like quenching wells while you're trying to develop them. And that's an ongoing process that industry is currently engaged with and trying to develop further. Overall, since I started working on these data sets and on these geothermal systems in New Zealand, myself and the people I've worked with over the years have hand selected something like over 30,000 borehole features, both natural and induced stress features, manually ourselves. So the research here and the work represents an impressive and dedicated amount of of effort and hours from a really amazing group of talented structural geologists and geoscientists. So this was great because we were finally getting the structural data we needed to talk a little bit more about these systems. But as we started rolling this tool out and running it in these high temperature geothermal wells, we realized there were some things that we had to adapt from how it's been run elsewhere, for example, where it's commonly run in oil and gas systems. We were like, we need to develop some processing and data analysis techniques that are specifically designed for these tools being run in geothermal systems. So a couple of so some of this is captured in a paper that was authored by Cecile Massio and myself and others on processing and analyzing high temperature geothermal borehole televiewer image logs. But a couple of the interesting things that we came across doing this in geothermal was, for example, when you're running acoustic images, because it's using sound waves in a geothermal well, sound travels differently at different speeds through fluids depending on how hot they are. So we had to adjust. So if we were trying to work out the borehole shape based on the travel time of an acoustic pulse back and forth from the tool to the wall, we had to calibrate that to the temperature of the fluid it was traveling through, which is something that normally doesn't have to be worried about when you're running these in lower temperature geothermal systems or oil and gas systems. Another interesting thing we came across was something we had to be worried about in terms of the orientation quality of some of the tool itself, because we were getting intervals in our geothermal systems that had high concentrations of things like hydrothermal magnetite, which throws off the magnetometers in the tools themselves. So you can see here, this is a log of the magnetic field flux in a lithology unit that doesn't have any hydrothermal magnetite. So it's nice and flat and fairly consistent. This had pervasive or disseminated magnetite throughout the lithology. So you can see it's a lot more wobbly. And then here is an example where we drilled through a dike that had a lot more magnetite inside it, high concentration magnetite, and it completely changes the shape of the measurement of the magnetic field here. And that's really important if you're using the magnetics to orient the geological structures and features that you're trying to characterize with this tool. So we had to develop workarounds and actually develop our ability to spot things like this in the adaptation of this technology to geothermal, to hot geothermal. We also had to develop our own classification system specifically for geothermal borehole imaging. And again, this is detailed in Massio et al. And it basically characterizes in a descriptive manner how we document and classify and order the data that we're able to get from these. And that had to be adapted from learning lessons and how other people had done it in different geothermal systems, but also how the oil and gas industry did it as well. And then we were also really lucky with one particular study that we did in New Zealand, where we had an exploration well that was fully cored and then had an image log ran in it. Because one of the things we were finding was that we had no way of relating the fracture signatures from different types of fracture fills to the type of geothermal mineral that that generates that sonic response. So for example, when we were able to directly correlate the core to the image logs, we were able to, for the first time, identify that when you get a low sonic amplitude response, that can either be an open structure, but it also might be filled with minerals like pyrite or iron oxides, or even hydrothermal clays that you find in geothermal systems like illite, smectite, kaolinite, that kind of thing. And then when we see these high amplitude sonic responses inside structures, we know that those are filled, but now with a bit of comparison to the core, that we were able to say that they're sometimes filled with calcite, they're filled with minerals like quartz, or even we found in one case, you can see from this thin section diagram here, this is a silicified clay-filled fracture. So we're able to now sort of get a sense for, well, we know what types of borehole image features might be related to exactly what the geological characterization of the feature is. And it allows us to do a lot more with the data. And there's a great paper that was led by Sophie Malloy and Katie McLean and myself that kind of summarizes some of the findings we got from this very unique study, because we don't often get to have a fully cored well alongside an image log. So we can collect a lot of great information from this technique, from the application of this technique to geothermal wells, but what can we do with it? And this was something this is what I've been working on basically for a long time now, is analyzing and interpreting the structural patterns that come out of these systems. And one thing we found, so here is the structural data that we interpreted from a paper we just published last year with a number of people in Tectonics, looking at the Wariki geothermal field and the structural information we were able to extract from borehole image logs here. So we had 4 different wells that we had image logs from in a particular region of the field. And what we wanted to do was characterize how the structure was influencing fluids, but also get a sense for what the structural architecture of that part of the field looked like in general, and how it related to the stress field and the fluid flow. And what we see when we start to analyze the orientations by themselves, so here we have some sterionets, and these are just contoured polar planes of all the different fractures inside each sterionet. So here I have at the top a sterionet for each well in completion. And then alongside that, individual sterionets for individual lithologies along that well. And when you look from well to well, you can see that there are significant differences and sometimes more subtle differences in the dominant structural orientations and wells that are drilled relatively close to each other. So for example, if we look at WK261, our dominant strike orientation is that northeast southwest rift trend that we expect to see, but the dominant dip direction is very strongly aimed towards the southeast. However, if we then move to a well nearby, which is WK266, what we can see is we still have that nice rift strike orientation, but now we're getting a little bit more of spread in the dominant dip directions, where we're getting a bit of a bimodal distribution instead. If we move to another well just nearby as well, now what we see is our strike orientations are no longer dominantly northeast southwest, although that population still exists. What we're seeing here is a much more dominant east-west trend. And when we found this, we were like, this is interesting because this kind of relates a little bit to what we were sort of thinking about with the fault mapping, where we were discovering a lot more presence of these east-west dip-slip structures, active dip-slip structures that we hadn't previously observed or mapped in the field before. Not only then do we see this variation from well to well across a small area, as we go down with depth, we see changes in dominant structural orientation as well. And again, all of this is important because if the fluid is flowing through these structures, it's being channeled in different ways through different structural networks because the structural orientations are different. So you're introducing variations in flow and anisotropy at different places within your field and at different depths within your field. And being able to characterize that becomes very important for how you then think about developing your operation or your drilling plans for this particular region. What we're also able to characterize as well are things like the fracture density profiles, which is what are plotted in the graphs along here against depth. And we're able to pinpoint regions that are intensely fractured and regions that are less intensely fractured. When we take some of the well scale information, and this is from another study that was done on a geothermal field just north of the Wariki one, the Rudakawa geothermal field. And this is work that was done in collaboration with some great people from Mercury Energy. We can actually start to get a sense of how we can use these fracture data to give us a sense of what the larger scale structures might be doing, the larger scale architecture of these structures. So here along the well in blue, we have structures that are dominantly dipping southeast, interspersed with regions where the dominant fracture orientation shifts to dipping antithetically northwest. So if we try and extrapolate what that general volume of fractured rock might look like away from this well, we can maybe get a sense of, okay, we're drilling through a region that is dominantly following the pattern of a nearby fault, which we know exists from larger scale studies of the field here, which dips in that southeast direction, which is dipping this way. So that's giving us this broad southeast dipping fracture population. But now with these interspersed northwests, maybe they are areas where the well is drilling through northwest antithetic smaller scale structures on that larger scale master fault, allowing us to maybe extrapolate larger scale structural patterns and give us a better sense of the structural complexity that sits inside these spaces. As I was saying earlier, something that is brand new that came out of running these tools in these systems was understanding the stress field. So when you drill out a well, you basically essentially create a cavity that's under compression because you've released the forces that were you've released the material that resisted those natural tectonic forces. And as that happens, it squeezes the borehole shut in a particular direction associated with the orientations of the maximum stress field and the minimum horizontal stress field. And that creates features in the borehole wall. It creates areas of extension where we get cracks forming, and it creates areas of borehole collapse, which create what we call borehole breakouts. And we can pick up the orientations of those induced features on the borehole images. So when we measure the orientations of those induced stress features on the borehole images, we can actually plot up the orientations of the stress field with depth along the well. And that's been very interesting, because what we can see is that the stress fields themselves are not as consistent as we often like to think they are. They actually contain a lot of variation, both at a very small scale of tens of meters to a well scale at kilometer depth regions, but also across a field as well. So for example, this is some more data from the Wairikee geothermal field. And what we can see here is that with depth, in the shallow portions of the well, my SH max orientations measured from the borehole features on the image log was more or less aligned north-south until a particular depth along the well where there was a shift, a small shift, in the orientation of that average SH max value. And what we also see is that when we look at the fracture patterns, here, if the SH max is north-south, we have a north-south population we have a population north-south striking fractures. But as we move away from that north-south directed SH max orientation, we come back into structures that are more likely aligned with the SH max that's shifting to a more northeast-southwest orientation. When you zoom in on particular areas of this data set, for example, you can see there's quite a bit of spread in the SH max orientations over very small intervals. When you zoom in to look at those intervals in a little bit more detail, what you can see are, here are my natural fractures, which create these sinusoids across the region. And here are my drilling induced tensile fractures, and which are my stress features. And you can see them changing orientation as they cross over these structures. This gives us the implication that these structures recently were active. They recently slipped. And the reason for that is when fractures or faults slip, they can perturb the stress field around them, which is what's being picked up by the varying orientations that the stress features are forming in. They're forming in response to a perturbed stress field. So we can identify structures as being recently active, and that's kind of important because recently active structures are more likely to have generated disparity in open space, which means they're more likely candidates for being modern day active flowing structures. And we can extract those from the data set and we can plot them up. And when we did that for the Wairikee field, what we found was we get active structures, or recently active structures identified in this using this technique, have that nice dominant rift trend that we expect. And then we want to look at the stress across the field itself and see if there's any variation as well. And what we can see is when we look at the orientations that we observe from the Wairikee field over here, we get a pretty consistent SH max orientation that's broadly northeast southwest, which is in line with what we expect for the SH max in this rift itself, with some subtle variations and rotations in between wells, which is interesting in its own sense. But as we move over towards the other side of the field, as we move this way, we see that there's a more significant rotation in the SH max, nearly into some places an east-west alignment. And that's interesting, again, thinking back to the idea that there are more of these east-west oriented dip-slip structures in the region than we previously thought. When we combine a lot of this information with indications of fluid flow that we pick up, so we can identify fluid flow zones along these wells using pressure, temperature, and fluid velocity observations. So when we map those out, and these are these shaded areas along here, when you map those out, we can actually then isolate the structural data inside each of these flow zones, and we start to get a sense of what actual elements of the structure network across this area or in this geothermal volume are contributing. And what we found from the Wairikee data was that it's a lot of the wide aperture fractures are contributing to the flow in the flow zones. We get clusters of active fractures, which makes sense to us. We also get the orientation of the structures that are in the flow zones, and they're dominantly either striking northeast-southwest or east-west. And previously, we've seen a lot of this in many of the other fields, but this is the first time we were picking up this east-west signal. We also get lots of high-density fracturing in these areas, and also areas where we know from the large-scale modeling, three-dimensional modeling of the field, where these wells have intersected faults. And then we can identify that a little bit more in detail. For example, you can use the images and directly correlate directly correlate fractures to large spikes in the temperature, so we know which structures are directly contributing, or clusters of structures, like here, for example, which are directly contributing this large temperature increase along the well. And we've also been identifying other types of features through classification that are likely contributing to structure or fluid flow in these systems too. Here, for example, is a resistivity borehole image log that shows us a nice conductive fracture fill, but with a resistive halo around it, implying that there's flow through that fracture that might be hydrothermally altering the wall rock around it. And we can also identify fractures that are open at least a little bit into the borehole wall by identifying open structures on the travel time images that are generated by acoustic borehole televiewers. Just to step away from that for a second, one of the things we can do with a lot of the structural data is we can take it to lots of really interesting spaces. So for example, we can explore statistical fits to describe andesite reservoir fracture attributes. And this is work that was pioneered by Cecile Massio, and looking at how well do the current understandings and our current expectations of the statistical relationships that govern things like fracture spacing or fracture density, how do they translate from the rocks that they're normally studied in to the rocks that we're interested in from a geothermal perspective? And what we're finding is that we're able to identify that fracture spacing, for example, in some of our reservoirs is a log-normal relationship, although sometimes some of the fracture orientations follow slightly different statistical laws. And the fracture thickness also follows a power law, except when you drop down to the microscale. So again, we're able to start pulling out these statistical ways of describing fracture sets from all of this data. And if we can do that, we can start to populate some really interesting models. So for example, we're able to take that fracture information and generate discrete fracture network models that we can then run flow simulations in, or even populate some of the fracture orientation and density and architecture information into flow models to understand how connectivity relates to the amount of flow through systems as well. If you really want to push the geomechanical aspect of this, you take a lot of that stress information and you combine it with other well tests and with other measurements, and you can characterize not only the orientations of the stress field, but the magnitudes of these stress fields. And if you do that, you can do some really exciting three-dimensional modeling to understand where fluid flow might be concentrated within your structural network in your geothermal system. And this is an example from a project I got involved with on the Astor Pass Greenfield in Nevada. And here we took the borehole image data. We used it with a bunch of other data to work out stress magnitudes and orientations. We then mapped those orientations and magnitudes onto three-dimensional fault models to see which parts of the fault were moving and which parts of the fault weren't. And then we combined that with some really great fracture information to identify sweet spots inside this volume that might be great areas to target for drilling this greenfield. So there's some really exciting things you can do with it. Then finally, I just want to pull this back to the bigger picture. So I started off talking earlier about how it's interesting thinking about this, the structural network and architecture in terms of a conceptual model for how geothermal expression operates inside the Taupo volcanic zone, or the rift that I've worked in. And we wanted to basically take a lot of the new data that we've been generating over a decade worth of analyzing structural networks in these systems with all the different new techniques that we've brought to bear to see if we could increase the resolution and increase the complexity or enhance the complexity that we know exists in these systems. When we look at the rift itself, and if you look at this map over here, we can see these little arrows. These are GPS vectors showing crustal motion and the direction of that motion. So across the rift, where all the geothermal fields are, you can see that there is a pretty much nice motion of the crust that gives us that northwest southeast directed extension, which is what we expect to see and what we expect from the rift orientation and the way the rift works itself. However, when you look at certain areas inside the rift, we also get this north-south directed crustal motion. And when we look at our borehole data, we get that SH max orientation that's northeast southwest, which matches really nicely with the extension direction this way that we've picked up here. But then we also see some borehole data that's supporting this east-west SH max orientation, which aligns with the idea of some north-south directed crustal motion or extension in certain regions of the geothermal systems. So if we try and extrapolate that up away from our areas and combine the stress observations, the GPS observations, all of the other structural data that we were gathering, and the stress data from the boreholes, what we're able to kind of see now is in the rift fill, where a lot of these geothermal systems are, it seems to be that the geothermal systems fall, at least some of them anyway, fall on areas where we get this intersection of northeast southwest rift trending structures and these new, or not new, but more carefully defined east west oriented structures as well. And we know that both of those structures undergo extension, pure extension, at certain times. So we think now it's the intersection between these two structures that is facilitating the occurrence of geothermal systems, at least within the rift fill. So coming back to the original, the existing conceptual model of how the geothermal expression occurs in this rift, it was relying on the intersection of the northeast southwest rift trend and this northwest southeast trend that is thought to be related to basement hosted large scale faults and observations on basement structures outside of the rift as well. So what we think now is maybe that is still the case for how fluids are being communicated through the basement levels of the Taupo volcanic rift. But as you move up into the rift fill itself and the material inside the rift, this switches to a tectonic regime that's a little bit more associated with the actual modern day rifting processes itself. Again, associated to much larger picture subduction mechanics, because don't forget, we're subducting underneath this too. So we think that it's this combination, this interesting combination of active structural orientations that might be facilitating at least some of the geothermal expression in the rift, but that might be fed by a deeper one. So we still have lots of questions about how this might link together and whether or not this system actually communicates down further into the crust itself. So we're able to start advancing our concept of this region, but we're still leaving ourselves with lots more interesting science that needs to be done. So that just summarizes up where we got to with this study and how we were able to extract borehole data at a small scale to try and give us some indication of what's happening at large tectonic rift scales. And what we see are that our intersections between the rift trend and the east-west trend create what we are referring to as regions of biaxial extension in the Taupo rift. And that in part controls geothermal expression here. And we are able to confirm those structural orientations within the rift fill and some of the upper basement by fault mapping and borehole imaging. It also confirms this east-west trend and that those east-west structures are dip slip as well. We're able to identify that fluid flow seems to be concentrated within these structural data sets. And all of this ties really nicely into a larger scale observations that involve GPS and some of the geophysical analysis too. Just to wrap up, and I hope I'm not going too much over time, but just to wrap up, I have a few finishing thoughts about the geothermal space itself. So one of the things I always think about with geothermal, because it is one of our key geological resources, if we are really truly engaged with the energy transition and with decarbonizing our energy sector, for example, I just did some back of the envelope kind of calculations to emphasize this. I think there's in some places there is not a lot of development in geothermal despite the promise it has. So roughly it costs something like 40 million British pounds to drill a 3 megawatt well and put a power plant in it. And that's not bad. It'll power at least a local region in some sense. But if we want to upscale that to, for example, bring a country into the gigawatt group, we're looking at maybe an investment of something like 13 billion British pounds. And that might, for example, fund something, or might be able to power something like 1.5 million UK homes. That's a significant impact on the way we use, on the way we power homes currently, mostly through hydrocarbon energy production, for example. If we compare that sort of costing to the way oil and gas, for the same sort of money, you can, and this again, very rough values, you can build a petroleum refinery in 20 wells. Now the energy difference and the energy output between these two is quite different. But again, we're in a stage where we are now looking at decarbonizing our energy production. So similar types of money can be used in different types of ways, depending on what our true goal is. But one thing I always think, and football fans, soccer fans are going to hate this, it's really interesting where we prioritize our investment as a people in general, and this is globally, when we're quite happy and willing to spend 140 billion British pounds on a sporting championship, but yet are incapable of finding money at times to install something that's really important for the future of the planet. I just want to touch a little bit on inclusivity as well. Again, it's really important thing to discuss, especially in terms of energy and geoscience as well. The best work and the best research is done whenever groups from diverse backgrounds get together and discuss ideas, and that's been proven time and time again in social studies. And I just want to highlight some amazing groups that are really doing their best to engage and encourage and enhance inclusivity and diversity amongst the, specifically inside geothermal, but in the general geoscience sector as well. And one of the main groups I want to give a great shout out to is the Women in Geothermal group, WING, an amazing group that champions inclusivity and champions the representation and encourages the representation of women in geothermal spaces, not just geology, but in engineering, business management, you name it. There's also Pride in Energy, which is a great group that deals with issues surrounding being LGBT+ in the energy sector and in the energy industry. And then I think you are probably have to have been living under a rock for the last year to have avoided the issues around racism that have become very strongly highlighted over the last year. But I just want to point out that there's great movements and groups that are in place to help deal with some of this. There's the Black in Geoscience group, and also from an energy perspective, there's the American Association of Blacks in Energy that deals specifically with issues related to the Black community, particularly in America, and the way it engages with the energy sector itself. So great places to go to encourage, think about, and work with and get ideas about how you can work on making the energy sector an even more inclusive and diverse space, which is only going to be a good thing. So just to wrap this all up, my own personal take on geothermal, and from my own experience working in it in 10 years, I've seen that it is a fast growing international industry. And I probably need to update this map since the last time we did it, but all these countries highlighted in green are countries that are either actively engaging in using geothermal power in some sense or form, or have active programs that are looking into developing it themselves, which just shows you the scope for what could be an amazing career as a geologist in the future. The resources that we're talking about, they require really detailed geological characterization at multiple scales, using multiple geological disciplines, if we're going to understand how they operate and how we're going to use them to our best advantage. And I believe that our community, the geological community, has an amazing wealth of experience and established techniques that we've been doing for decades that we just need to work on transmitting and translating to this growing industry of geothermal. From what I've found working with industry, working with government, working with research, the research community, is that there is a lot of room for innovative thinking around how we adapt a lot of our geological expertise to the exploration, development, and operation of geothermal systems, and that within the industry, there is a great opportunity for you to be innovative and think about new ones as well. So if you're interested in geothermal energy, especially as a geoscientist, I think there's an amazing potential to develop an exciting and lucrative career in this sector. Thank you very, very much for having me talk. It's been a real pleasure to be here and to have given the last talk of the season in a festive way. And finally, thank you to everyone who's ever supported the work I've ever done over the last while.
Thank you very much, David, for such an inspiring. I learned a lot, and I'm sure everybody else as well. There are already plenty of questions out there. I wanted just to take the chance and also appreciate the slide you showed for support of diversity in geosciences. I think that's extremely important, and I'm really delighted that you had this already announced here. Thanks a lot. Sebastian, is your turn.
Yes, thank you very much for a great talk to end what has been a long year for everyone, and a long series for our geoscience and GeoEnergy webinar, which have happened over just a friendly chat on WhatsApp between Hadi and I along what seems an eternity ago. So thank you for closing out the year here. Again, just let me reiterate what Hadi's mentioned. Also, thank you very much for highlighting diversity and inclusivity issues that we all need to tackle as a community. So there's much work to be done. So thank you very much for this. What surprised me most, and I'm going to take very, very briefly my privilege of sharing the Q&A sessions, is I've always thought we just stick the usual tools down Borehole to get the data we need. And so it wasn't really on my radar that there's so much work to be done. Just a very quick question. Compared to your average oil and gas reservoir, does the temperature that we have, the 300 degrees, does that change anything in terms of the resolution, how we measure fracture apertures, cutoff values, etc.? Is that fundamental
it can do,
difference?
particularly with the borehole with the acoustic televiewer, because you're using sonics. If you're in fluids at 300 degrees centigrade, you're maybe dealing with dual phase, or even possibly supercritical. And again, understanding how that is influencing that passage of the sonic pulse is really important, or whether the sonic pulse is actually making it strongly enough through from the tool to the borehole wall, especially if it's moving through a vapor dominated interval along the well, for example. So there's definitely a lot more that needs to be looked into with regards to how we apply this technology to some of these systems, because we're not used to working in, I hate this term, but everyone uses it, volatile kind of environments. And it's not just the sort of the physical impacts that can have. There's the chemistry of these wells can be crazy sometimes, and that does all sorts of interesting things to the materials that are used to make these tools. So there's definitely a material science space that needs to be grown here about how we develop tech for these systems as well. It's a really interesting space. I got to work with some interesting engineers once on who specifically design sonics and sonic generating equipment and how that responds to temperature and stuff. So there's some really cool places you can work in collaboration across disciplines inside geothermal because of things like that.
Yeah, and especially I think as we go to these hotter and hotter systems, I think about Iceland deep drilling project. Okay, let's go to our audience. I'm going to start chronologically and try to group the many questions that have come through. So Milad Nadelo was the first one to ask a question. Said, very interesting work. How can you characterize the properties of the faults, especially flow and heat transfer properties? You mentioned very early on some of the deeper work, some of the deeper
it's a great question. Again, we sort of at the stage we've kind of I pushed some of my work to, I guess. We've looked at we know which structures are flowing, but again, measuring precisely what the flow is out of that individual structure. Again, it needs more sophisticated tools that we can put down there to actually capture that, or maybe the development of packers to isolate those so we can, characterize it. I mean, I think back to I kind of think back to processes like maybe drill stem tests and that, where you would isolate an interval of the well to fully understand what the pore pressures were. Maybe there's a way we can adapt some of that to understand the flow inputs from specific structures that we identify using the techniques I've shown today. But it is quite a difficult. Those are very difficult parameters, I find, to quantify at this stage. And I know people are working on it. It's not something I've delved too deeply into myself, but it's a great field that needs a lot of expansion, I think.
Okay, great. That's really interesting. So I'm just trying to find the next logical question here. So just on what we measure, Yuan asked a question, and thank you for the very interesting talks. The way to connect the low range with highly accurate borehole data with seismic data to improve the characterization.
With global seismic, interesting. I'm not sure. I'm not sure how the data sets at the scales that they're being picked up at would marry together. It would be interesting to explore that idea, but I guess the global seismics, you're dealing with something on a much bigger sort of scale, especially the scale of measurement of it as well. So being able to isolate that down, the microseismicity studies, like the example I showed that was done by Fabian Sepulveda, that shows a nice way of possibly being able to at least identify microseismicity associated with the operation of these fields, potentially around individual or structures as well. And there's some other great work that's been done in New Zealand by Stephen Sewell in the Rotocala geothermal field, looking at seismicity migration across structures as you inject and extract. But I'm not sure how I would marry a global data set to that level of investigation, but it will be interesting to try.
Thank you. Again, so colleagues, audience wondering what we can measure downhole. Arthur wonders, and thanking you for the presentation. His question is it possible to measure or characterize any fault, slipstick behavior, determine friction coefficients, etc., with the borehole data? Or is that something you always need to go back to the lab for that?
But yeah, my go-to would be the lab. Mainly because they're just fun experiments to do. I guess again, maybe with the development of I mean, we see a lot of people, especially now with a lot of interest in sort of fault drilling projects. So I'm thinking, some of the stuff I've done with the Alpine Fault Group and some of the big scale work that others are doing in that space, developing tools or tech that can be put in place into the boreholes that will actively capture things like strain and slip associated with, ongoing crustal movement. But in terms of capturing it and then bringing it back out straight away, I'm not sure how that would work. I mean, definitely my go-to is the lab whenever I want to do that. But it's if someone could come up with a way of doing it, that would be pretty interesting.
Yeah. So going to a little bit to the data that has been measured, and Christine has a number of questions, and they're all interconnected, and some other people follow up on this, on the actual data that you measured. So the first one is the shift in the SH orientation. Is it also affecting the density of the fractures or just the orientation? And bringing up the second question, she also wonders how wide are the fractures? What's the average aperture in them?
Sure, Christine, great. That was a really interesting sort of we tried to see what that relationship maybe was between stress shift or stress rotation or perturbation and the density of structures, and there was nothing systematic in the data that showed that X definitely causes Y, for example. But what would be worth a little further investigation is, are the rotations in the stress field generated by larger scale structures, which in turn are also associated with high fracture densities as well, because of the damage zones around those being a lot more intense than being further away from the large scale fault. So if the stress orientation is associated with the large scale structure, it's likely also to be interacting in some way with a higher level of fracture density. But again, from the data we looked at, there was nothing systematic to suggest small scale relationships or relationships that I just mentioned. Aperture wise, the widths you can measure are limited by the lower resolution of the tool itself. So you're maybe thinking it's like a centimeter or 2 centimeters, maybe roughly around that size for your minimum. And then we were able to see structures that had tens of centimeters width to them as well, some of which we could tell were filled, but some of which also appeared to be potentially open structures at depth, which was fascinating. But the tool resolution has a kind of restriction on what you can see, I guess, in terms of the width scale.
That's quite a fascinating thought that I'm working on the field as well at the moment, where you have fractures that are several centimeters, possibly more than 10 centimeters open, kilometers deep on the subsurface. I'm still trying to get my head around this, because also all the modeling then feels over this, try to stick those mega permeabilities into
or even just the concept of an open space with fluid in it being able to remain open at kilometers depth is kind of it messes with your brain a little bit.
David has a question again. A very nice work and talk. How would you differentiate between drilling-induced structures from the natural active structures in fields with limited wells that could be used for correlation?
Good question, David. And the very glib answer is with difficulty. There's a couple of wells I've worked on where I felt like my eyes were going to fall out of my head. I was trying so hard to determine, is that natural or is that something that's been induced as part of the drilling process itself? What is great though is there is an amazing global community of people who work on these images, and people who have been looking at them for way longer than I have, and they're really approachable whenever it comes to sharing, hey, look, I've got this, I think it's this, what do you think? And there's a great community out there that's really more than happy to give you their opinions as well. So it's a nice, in one way, there's a lot of people you can bounce that around with, but it can be quite challenging at times to isolate induced from natural, and then also to sometimes separate whether the natural structure appears the way it does because it's aligned nicely to be put into motion by the stress field. So you have these what they call stress aligned or induced aligned structures, for example, as well. So it gets complicated, and it can be quite a pain to come up with your kind of line between those two things sometimes.
Yifan is a really interesting question. Thanking you for the talk and the encouragements. And, asked, do the fracture orientation and the local earthquake focal mechanisms confirm each other? Does the stress field change during geothermal production? So what does your data tell you there?
That's an awesome question, Yifan. Thank you. Earthquake focal mechanisms, I guess, watch New Zealand geothermal space. There are people that are kind of looking into that. I mean, they're measuring seismicity in quite detailed ways. So there has been some initial studies into focal mechanisms in these fields, and the little bit that I've seen, the little bit of the results from those studies I've seen so far does seem to fit with what we're seeing. Certainly, some of the larger earthquakes that have had focal mechanism work done on them in that region point towards an SH max aligned with the rift trend, which is what we dominantly see in the well data too. In terms of the stress field changing, because as you do things to the geothermal field, as you inject or extract, we know that the seismicity of these fields changes as you inject or extract. I mean, I think that's just a given at this point. If you're putting anything into or taking anything out of the ground, especially fluids, you're going to make seismicity happen. And so we can definitely see that geothermal operation does change the way the field behaves seismically. And I guess in a kind of linked way, if there's enough seismic activity perturbing the stress, which perturbs the stress field, maybe maybe that activity is causing small scale rotations in the stress field as well. That's a really good observation. Interesting.
Thank you. I'm going to shift gears for the last group of questions. I'm going to group, and so the considering the time, group the questions, and this is of the knowledge transfer. And there are a number of questions that came in from, and I'm pulling them out one after the other. But Leila, Sarah, and Kishan, they sort of wanted the workflow that you've introduced for geothermal fields. How could we use that for gas reservoir, for CO2 storage site, for hydrogen reservoir, where we do have fractures, where to have the reservoir response to where the reservoir is fractured, we need to understand the fracture characterization. So how does your tool help you, your workflow help you to obtain more realistic stress fields in other subsurface energy applications?
Yeah, I mean, it's one of the things I've enjoyed a lot, I guess, about the work I've got to do adapting these techniques to geothermal is that the sort of takeaway message I got from my work is that these tools and techniques are completely adaptable. If you want to understand the subsurface, you want to characterize it. So anything you want to characterize, look at who else is doing it for different reasons in another industry or another field, and go, that's really good. They're generating the type of data I need. How do I take that and put it into the system I want to work with? And I think we can do a lot more of that. I think, the petroleum industry has generated a wealth of technology, geological expertise, training, and skill development for many, many years. It's produced computer software and modeling that is just top of the game for doing what it needs to do. And it's part of the things that for all these new systems and new subsurfaces that we're trying to develop, we don't have to reinvent the wheel in some ways to do it well and to characterize it well. We just have to take what's been done elsewhere and work on adapting it. Now, there's probably new things we can still develop too, but there's so much that's already been done. We just need to be smart about how we transfer it across. And I think there's so much of that yet for us to do, especially for all these new systems that we're getting more and more engaged with, like geothermal and CCS, or any form of underground storage, really, as well.
Thank you. Yusuf has one question. It's probably the multi-billion-pound-dollar question. Do you think geothermal systems have the potential to replace oil and gas?
Maybe if we're willing to stop having really expensive football tournaments. I don't know. I would love it if it could. I think it has a huge potential. And again, I mean that in the sense that, you know, it's not just about the electricity consumption. It's you know, it's about how we power everything else, how we heat our homes, how industry uses energy as well. I think it has the potential to significantly contribute. Whether by itself it could replace, I'm not sure. I would be hesitant to say that, but I think it's an important part of the energy transition. It's an important part of the future that we're all interested in getting ourselves to, and because it kind of provides a stable baseload production, I think it's kind of one of our reliable options for developing. That's not sort of as subject to the tides or the winds or the amount of sunshine we get. I think it forms maybe a really solid base for which we build a more diverse energy provision society on. That would be the way I would envision it anyway. But it's going to need a lot of work from great geologists, and it's going to need a lot of investment from government and industry. So if you're from government or industry, please give money to geothermal.
Thank you. I think these are sort of all the key questions, but I'm considering that you're sitting in front of this nice Christmas tree. I'm going to ask you one final question. So if Santa, and this goes back to one of the very, very first talks we had in this series, which was by Inga Barrow, who talked about sort of the next generation of geothermal modeling. And Inga was just learned yesterday that she won one of these EU consolidator grants, which is tremendous.
Congratulations.
Congratulations.
Yeah.
So when Santa comes, David, and asks you, what do you wish from the modelers to provide you with, so you can actually better model the data? And this is with Hadi being a mathematician, me being an engineer. What is your wish list from Santa to Hadi and myself, so you can model your data better in the future?
That's a great question. Mind is spinning now. I guess because there are so many different things to characterize and there are so many different processes to understand, I guess what I would love from modelers is, what's your priority? What's your top three things that you need more data on and more understanding of to really take your models to the next level? Because I could spend the next 5 decades of my career, if it lasts that long, exploring any range of characterization elements or processes, understanding any sort of processes in these systems, but they may not have huge amounts of impact on the models that we're using to govern how we operate and work these systems. So yeah, from a feedback pathway, give me your top 3 parameters, and that's what I'll try and work on.
Great, thank you much. With that, thank you again for a fantastic talk, David. Thank you to the audience for great questions. And I hand over to Hadi for some very wise words, I hope, to close out this year's GeoScience GeoEnergy webinar.
Yeah, thanks a lot. Thanks, everyone. I really enjoyed all of you as well, the great talk and the conversations. I'd like to first take the chance to say that this was the last live talk of this year, 2020, and next year we start on 7th of June with Roland Horn from Stanford on geothermal field developments as well. So that would be the start of next year, 7 June. Until then, you stay all, please, happy, healthy, but also submit your 10 seconds video to us as soon as you can. And the scene David is sitting there, it's awesome. David, please record yourself before you change that scene. And others as well, wherever you are, it would be great if we receive videos from China, from Africa, Mexico, Indonesia, and Europe, US, and everywhere else, Middle East. Please do send them all to us. The email address was already typed up there. We are going to post it in our Twitter and LinkedIn account. This is gse-citg at tudelft.nl, and please keep the subject as mentioned there, because our colleagues would expect that those emails would go and land in a special folder. Otherwise, Sebastian and I should go and assist them to find your emails. So with that, I take the chance to wish you all the very best of the best holidays ever. You all deserve that, and stay happy, healthy. And I would like to ask David and Sebastian also to have some sort of final end of the year message to you as well. So from my side, all the very best. It has been an honor for us to host you all, 35 great speakers during the pandemic period. Sebastian.
Yeah, so thank you very much, Hadi. And again, thank you everyone for listening in on a weekly basis from wherever you are, for all the 35 speakers who really bridged across a very wide range of topics, from geothermal energy, fracture characterization like David's, to the more fundamental issues around climate change. Where do we head in the energy transition? I've learned an awful lot. And looking back when Hadi and I sort of thought, well, we could just give a few talks to each other's research groups. That was how it all started out, and that we now have 1,600 plus viewers. We've never thought that webinar series has such an impact, such a reach. So it's really a pleasure, honor, and privilege to organize this and work with all the great speakers, and know that there's so many people who enjoy listening to those talks. So stay safe, stay healthy, enjoy the holiday season. I think most of us, we're running on fumes as the end of the year approaches. So I hope everyone gets a really well-deserved rest, can recharge batteries. And here's to more positive, less eventful 2021, where hopefully we can see most of each other at one point in 3D, at a conference, for a walk at the universities, in a cafe, in a pub, wherever we want to, and just continue talking science, talking energy, and supporting our community. David.
I guess I get to close the show. I guess I first want to really thank Sebastian and Hadi, not only for inviting me to speak today, which is a great honor, but also this webinar series has been a really great and fascinating way to engage with a very global community, and to really sort of enhance the accessibility of some great science right across the world. So it's been a really amazing endeavor that you've started. So you should really be very proud of this. I've certainly enjoyed watching a lot of the talks over the last few months. So thank you very much. Thank you for letting me be a part of it. And I guess to everybody watching, happy holidays, and enjoy a few weeks off work if you can. And let's look forward to a great 2021. Thank you very much.
Thanks everyone.
Bye-bye.
Bye-bye. Until next year. Bye-bye.